welcome back. In our last lecture, I introduced you about the scanning probe microscopy, and today we will begin with one of scanning probe microscopic technique called scanning tunneling microscope. And we will go first to see what the different components of the scanning tunneling microscope. Just briefly I will tell about the principle and then the different parts of STM and in this lecture today. Scanning tunneling microscope, as the word suggests, scanning means a physical probe is there which will scan over the surface, providing us the information at the atomic level or microscopic level. That is why we are telling it microscopy. We get in images of the object at the microscopic level, and the middle one is a new word, that is tunneling. Here tunneling word stands for measuring the tunneling current. Tunneling current is measured between the current flows from the sample or specimen to the tip or tip to the sample. A current that flows via tunneling mechanism is called tunneling current, and by measuring that tunneling current, as you see, the principle of the STM is to move the sharp tip close to the surface in order to measure the tunneling current. Tunneling current can move to the sample or out of the sample, and that is done by applying a bias voltage, And in these cases, as we are going to measure tunneling current, the tip has to be conducting. Therefore, we use a metal tip as a probe, and also sample must be conducting. Sample has to be conducting. So, this is the primary requirement for scanning tunneling microscope, or in order to measure the tunneling current and using the tunneling current to create the 3-dimensional image. And the tunneling current depends on the position of the tip above the specimen, where it is positioned and how close it is positioned to the specimen, and also to the applied bias voltage, and also local density of states, whether density of states at that place of in the specimen is high or low. So, the current depends on all these factors, and this microscope provides us the resolution better than 0.1 nanometer laterally and depth resolution 0.01 nanometer. So, as you see here, we have a metallic tip and a conducting sample. This is the must for scanning tunneling microscope. In previous microscopic technique, let us say scanning electron microscopic technique, we are using electron beam, and if the sample is metallic, then is no problem. If the sample is insulating, also we can do if we do a metal coating on this specimen. If a metal coating is provided, then charging does not happen, we can get surface morphology. In the helium ion microscope, also we can do non-conducting or insulating sample much better than scanning electron microscope without doing the metal coating. Here in the helium ion microscope, there we were using a electron float gun to neutralize the charges in the helium ion microscope and able to study the insulating sample. But here scanning tunneling microscope, sample has to be conducting. We cannot do metal coating here to study the surface properties of this specimen. Why? Because here we see the surface atoms. If we do the metal coating on our sample, then actually we will see that metal coating rather than the actual material we want to study. So, we have tip, we have specimen and a bias voltage, and then other things like feedback controller, all other components we will discuss what are present in the specimen, what are present in the scanning tunneling microscopic technique. Here is a schematic diagram of scanning tunneling microscope. We have a tip here, and tip is mounted on a piezoelectric tube or piezoelectric scanner. Tip is mounted on a piezoelectric scanner, and then these are two things. Then we have distance control and scanning unit. Distance control and scanning unit will make this tip to go up and down, control the gap between the tip and specimen, and also to scan over the specimen. And in the process we measure the tunneling current, because tunneling current is very small. We have amplifier to amplify the measured current, and that to be converted to voltage, and we measure the data out of it, and that data is used to create 3-dimensional image. So, we have distance control scanning unit and the data processing unit computer to create image. Another important requirement for this microscope is vibration isolation system, because here the tip and specimen distance or gap is less than 1 nanometer, very small. Therefore, any vibration, any small vibration is not accepted. It should be completely vibration free. Then only we will able to get the precise and accurate data of the specimen surface. So, we will go to discuss on each components of a scanning tunneling microscope and how they play a role in the performance of the microscope. First is the probe or tip. The tip are usually made from tungsten metal or platinum iridium alloy. Even it is only single platinum also used, or PT is also used, PT metal, platinum, all platinum iridium alloy. At the very end of the tip there should be only one atom. So, if the measurement has to be done on the ambient condition or under air or liquid, then this we should need platinum tip or platinum iridium tip. On the other hand, because we cannot use tungsten if we have to do measurements in the liquid medium or in the open atmosphere, because tungsten will oxidize. The surface of the tungsten tip has chances to get oxidized. Once it get oxidized, it become a insulating or less poor conducting, as we measure here tunneling current, which is not accepted for the tip to be non-conducting in nature. For the measurement in high vacuum, we can use tungsten metal as a tip, but not when we will study the material surface properties under air or liquid medium. Scanning tip is most important aspect of this STM, as tunneling current is carried by single atom, and atomically resolved images are obtained, atomically resolved image is obtained only when tip have a single protruding atom further than all other atoms, which we have been telling repeatedly for this type of measurement. Then the after tip we have a piezoelectric scanner. Piezoelectric scanner on which tip is attached or mounted. So, this is a piezoelectric tube scanner. So, here is a piezoelectric material, this is a piezoelectric tube, and this is a metal electrode. Piezoelectric materials are mostly insulating material, ceramic material, and therefore, this piezoelectric material undergoes contraction and expansion. The contraction expansion of piezoelectric tube occur when electric voltage is applied due to piezoelectric effect. We will come to more detail about piezoelectric effect soon. So, the contraction expansion of the piezoelectric tube occurs that makes the tip to go away from the specimen or also move in the xy direction. So, the piezoelectric tube scanner makes the tip to move in xyz direction. By adjusting the voltage on the piezoelectric elements, the distance between tip and surface is controlled, and it has 4 quadrants like x minus, x plus, y plus, and behind that y minus, and they can move together or independently. If they move together, then motion occurs in the z direction. If they move in a single way, then they can move independently either in x direction or y direction. So, this piezoelectric material is used as a scanner in the scanning tunneling microscope. Then we have a distance control and scanning unit. First we have a coarse control. Of the tip to position the sample surface before the piezoelectric tube start functioning. We have a first coarse control is there, and then the fine control is done by piezoelectric scanner. We have vibration isolation system then, because we deal this deals with atomic resolution, where tip moment is in the sub nanometer distance. So, the isolation of all kind of vibration are important. Tip to sample distance must be maintained at a distance of 0.1 nanometer to get high atomic resolution. Therefore, the vibration isolation system is highly essential. Due to the high sensitivity of the tunneling current between tip and sample, it is absolutely necessary to reduce the inner vibration. Inner vibration means the system vibration or microscopic vibration, while isolating the system from external vibration. There can be external vibration, building vibration, noise, electrical lines, all these kind of systems can produce some kind of vibration. It should be there should be no vibration, so any kind of vibration. In addition that the system itself should not have any vibration. Then we have data processing unit or display unit. A computer records the tunneling current between the specimen and tip and controls the voltage to the piezoelectric tube to produce 3D image of the specimen surface. First, we will see how that tip is fabricated for an STM, scanning tunneling microscope. Normally, for the scanning tunneling microscopy study, the operator or user himself or herself prepare the tip. It is not normally commercially purchased. It is not commercially purchased. A fresh tip has to be fabricated to get the information at the atomic level or the correct information. So, and the resolution of the STM depends on how sharp is the tip. It is essential that tip has to be atomically sharp, having only single atom at the apex, because a blunt tip will reduce the resolution because it can cause electron tunneling to occur on a wider range. If there is two atom, then we will always get current both places. That means, our resolution is now not atomic level, rather diatomic level. So, we can only, and if I have a single object here, single tip is here, and I have a diatomic tip at the apex, then my current will be seen as like this, because both places, both the atoms will detect the current and thereby providing resolution of this much larger size in the diatomic scale. Tip should have smallest radius of curvature at the end and a narrow diameter to explore the trenches and pits on the surface. The tip should be stable at a given electric field, because we apply the bias here. So, when we make a atomically sharp tip, that should also stable with the applied field. There are different ways these tips are produced. One can do mechanical coating, ion beam milling. This kind of coarse method can be used if we want little flat samples to study. On the other hand, if normally and more often electrochemical etching is used to produce the sharp tips in the STM. So, most commonly electrochemical etching technique is used to produce tips for or probe for STM. So, how the process of electrochemical etching is done? The electrochemical etching is done in a basic medium, either sodium hydroxide or potassium hydroxide solution as an electrolyte, and we have this is in tungsten, we have a tungsten as a cathode as a anode, this is anode, and we have a cathode. Cathode can be stainless steel, can be copper, and we apply a potential. Upon applying the potential, there will be etching. The wire will etch at the surface of the electrolyte. At the meniscus of the solution, etching will be occurs, and when this etching occurs, it will produce this is sodium, not sodium, this tungsten oxide WO4 minus, it will produce here WO4 minus anions. This is a little heavier, and due to convection, the fresh OH ion at the electrolyte and air interface will flow in the downward direction, and these heavy anions will come downwards, and that will protect the wire at the bottom towards the bottom side. And once etching completed, this wire will fall down due to its weight. The wire, once etching enough etching is done at the interface, slowly after some time it will fall down due to its gravity or weight. And as soon as the etching process completed and the bottom parts fall down, the voltage applied between the cathode and anode should stop to get a very sharp tip in the upper part. If the voltage is still applied to a few seconds, then it will make this tip again blunt. So, as soon as etching process continue, as soon as etching process completed, and when the bottom part fall down, the voltage should be stopped to get a very sharp tip. And you see in the right side diagram here how a sharp tip is obtained. There is also another design where a copper wire, it is a copper wire is bent, this is a copper wire is bent in as a form of circular ring, and it is used as a cathode. Then this is our tungsten wire. This tungsten wire is normally of diameter 0.25 mm. Initially a tungsten wire of 0.25 mm diameter is taken, and then by applying the potential, where the ring served as a cathode and the tungsten wire served as anode, and it produce it is done, the etching is done, electrochemical etching is done to obtain a tip or probe for the STM measurements. It is also in the basic solution. So, to create a sufficiently sharp tip, the etching important point is that etching must be stopped as soon as possible once the tip is formed. This is very important. If etching continue and this application of the potential continue for a little longer time, then tip will get blunt. A typical benchmark for a good STM tip is the radius of curvature around 50 nanometer or less at the tip apex. The sharpness of the tips depend on the operation of the cut-off circuit. It is very important, and how fast it is, and limited by the speed of the circuit itself, and the reaction that follows here, for making a tungsten tip cathode, we have it is in aqueous solution, 6 H2O plus 6 electron, it will produce 3 H2 plus gas plus 6 OH minus, and at anode, which is tungsten, it will be provided with OH minus ion, which will produce an ion WO342 minus and plus H2O plus electron, it will be power H2O 8H6E, and overall reaction is like tungsten plus 2H minus plus 2H2O is equal to 3H2 gas plus WO for 2 minus. This was the overall reactions in the etching process. So, once tip is formed, it is normally cleaned with first deionized water, and then there are cleaning process. First is it is heated under vacuum, and resistive heating is done first. Resistive heating can be performed to remove the oxide layer, because it is done in aqueous electrolyte. So, some oxide layer will form at the surface of the tip. So, resistive heating is done to remove the oxide layer, and other contaminants from the etchant, like we are using sodium hydroxide or potassium hydroxide, some sodium or potassium salt might be sticking on the tip. So, the resistive heating will remove that. A direct current is applied between the tip and another tungsten wire touching at the tip, and the tip is heated to a temperature above 800 degrees centigrade for several seconds to clean the surface. There is other process of doing it also, like it can be done by sputtering, by ion bombardment, such as argon ion bombardment of the tip under vacuum. This also can be done. One can also apply high field. A voltage is applied between the tip and the sample, tip at the positive voltage and sample at the negative voltage, to remove and clean the surface. This is what also we have seen our field ion microscope. If you apply a much higher field, then the surface atom will be evaporated and removed. So, in that process also, by applying the high field to in a controlled manner, we can clean the tip of the tungsten. And once it is done, one can know whether it is a very sharp tip or not by doing a field emission measurements. One can take this tip, and then take another tungsten wire, then apply a potential potential between them. If it is atomically, then when these two will come closer, let us say this is tungsten, one can use another tungsten. So, when these two will come closer to each other, then current will pass, current will tunnel between them. So, because electron will be emitted from the surface of the tip, because it is atomically sharp tip, a very high field will be concentrated at the tip, and it would emit the electrons. And if we could measure a current of around 1 nanoampere at a voltage of, let us say, at around 600 volt, then tip is sharp. If we need higher voltage to achieve 1 nanoampere of current, that means the tip is not very sharp or atomically sharp. One can do a measurement or testing to make sure that whether atomically sharp tip formed or not. In other way, one can look at under microscope and check whether tip is sharp or not. So, in this way the tip is fabricated for the scanning tunneling microscopy. So, in conclusion, what we have seen here that we have a probe, sharp probe, that is nothing but tip. This tip is either tungsten or platinum or platinum iridium alloy. Tungsten tip is used if our measurement has to be done in vacuum, On the other hand, if measurement to be done in ambient condition or under liquid, then we should use platinum or platinum iridium alloy, and these are all metallic tip, because one of the requirement of scanning tunneling microscope is that the both sample and tip should be conducting, because here we measure the tunneling current. Then we have a piezoelectric scanner. Piezoelectric scanner is nothing but a piezoelectric material, which is a ceramic material that undergoes contraction expansion when we apply voltage, and that allows the tip to go up and down or left and right, x, y or z movement. So, piezoelectric scanner does the movement in a finer manner after the coarse control is done by the controlling unit, and then we measure the tunneling current between the tip and sample. So, therefore, the tip scanning unit, that is a piezoelectric scanner, and tunneling current measurements, all these three play important roles to create surface images, 3-dimensional images. In particular, the shape of the tip has a pronounced effect on the image resolution. So, we must have a atomically sharp tip to get atomically sharp image. The STM tip is most commonly fabricated through electrochemical etching in a basic solution. So, we use electrochemical etching as a very common or widely used method to fabricate the tips for STM. The references. Thank you.